So we got a lot of assembly programmers on here. We're going to be jumping into our new segment that's happening now, which is assembly language. And so our very own Mr. Steve Bjork is working on a nice introductory crash course to assembly where we're going to learn things in baby steps. We're going to build a foundation, and we're going to learn the language. So this is cool stuff. I am going to go ahead and now switch over to the presentation, and we're going to let Mr. Bjork tell us what is going on here with our latest entry into this new segment. How about we play a little bit of Curtis's custom music here to start it off. Woo! I like the sound of that.
Just about woke me up.
Well, hopefully you won't have to play that again after I'm done, because I put the people to sleep. Any case, this is definitely lesson number 2. We're still in the foundation section. Now we're going to talk a little about memory. And as I said, we're going to keep this stuff short and sweet each week. We're not going to get bogged down in a lot of details, just enough foundation. And then we'll actually get into the actual writing stuff in assembly. But there's just some stuff that you need to know. And why don't you go ahead and go to that next slide.
Okay.
Well, as we talked about before with lesson 1, information is stored in the computer as numbers, and it doesn't use the same sort of numbers that we're typically used to, like 3.14159. I won't do that to you, but basically
right?
real, yeah. But I could do it up to about 100 places at one time. And then I gave up when I had a friend that could do it to 500, and I said, oh, that's a little ridiculous. Anyways, but the computer works with numbers that are basically binary, on and off, and we can put bits together. That's the individual ons and off, and typically the 6809 uses 8 and 16-bit numbers. So it's very easy to do a number from 0 to 255 or 0 to 64K. And this is basically how the computer stores its information in general, as numbers. You can do calculations, you can reference things, but this is basically how that does. Now the thing is, we've talked about numbers, but where in the heck does the 6809 put these numbers? And that's what we're going to cover today, is basically where you could store your information and your numbers in the computer. Now, there's 2 places you can do it in a 6809. The first one, that's real simple, really fast, is what we call the registers. These are storages that are built inside the computer that you can reference in assembly language. You've got the A and B accumulator there for doing math work, when you're adding information together, comparing, and like that. Then you have the X, Y, U, S, and the PC register. PC stands for program counter, and the direct page. These registers are used for referencing where in the outside memory things could be used. They could also be used for doing 16-bit math too. But this is stored inside the CPU, and it gives you instant access to that information. Now then, there's another thing called your 64K of memory that's out there. And basically with that, you're looking at, you got a lot of places you can store stuff, a lot more than the few that you have in the register. The problem is it is outside, and it takes a little while to access it. And why don't we go ahead and go to the next slide now.
Okay.
This here is a little graphic I put together that kind of shows what's inside the CPU, showing the registers, and then talking the outside. Got somebody with a very noisy mic out there.
I think it's pull button.
Getting a little bit of a ground hum there.
Yeah.
Okay.
Anyways, getting back to that. The reason why it takes a while to get to the 64K of memory, as said, it's outside the CPU. The computer actually has to go out to the ramp, grab it, and come back in. It's a much slower process than just using the internal CPUs. Think of it kind of like, and I'm going to steal this one from Curtis. You got a tool belt on you. You're doing work around the house trying to fix things. The tool belt's handy because the parts are there. Your tools are handy to get to, but you have a limited number of slots on your tool belt that you can carry things around. And so when you're doing your project, you load up the information that you need, the tools, on the tool belt, and you go out there and start work. Well, all of a sudden you realize you need another tool. Don't have the space on your tool belt. You've got to go outside to your garage and get your tool from there, and then go back to work. You can see having to get that tool slows down your work. But see, that's the reason why we've got this extra memory outside the CPU, is so that you can have lots and lots of tools. It just takes a little while to get it and bring it back.
Gotcha.
That's pretty much what's going on is you have this limitation between inside tools and outside tools. Now the 6809, it's much better than the 6502 in that respect, because it only really has like 4 tools or 4 registers inside the CPU.
And they're only 8-bit.
Yeah, and they're only 8-bit. Takes a lot of work. 6809 is mostly 16-bit tools, and you got a lot of them. Now, of course, the 68000, the big workhorse computer processor from Motorola, that had 16-bit registers, and that meant that you basically had a big tool belt on there.
Yeah,
and that helped. So that's the thing is, as the processors got better, they had more slots on their tool belt, so that you didn't have to keep running out to the garage to grab that extra tool. So that's really what's going on here. Is we have to, later when we get into actual assembly, we're going to be looking at these quick things on your tool belt compared to the stuff that's stored out in regular RAM.
Okay.
Let's go ahead and go to the next slide. Well, the advantage of using internal registers, we pretty much went over. It's, you don't have to take the time to get the information from outside the CPU. Commands like increment A, basically that's working on the registers that's inside the computer. The instruction is just 1 byte. See, that's the thing about the 6809 processor, is that instructions can be anywhere from 1 byte to about 4 bytes. There's exceptions, and we'll go into that later. But, the more bytes that an instruction takes, the longer it takes to execute. You have to go out. But the thing is, the internal registers you can work with very quickly. And by the way, in the case of the increment A, that's only takes 2 clock cycles. Everything in the CPU is done on these clock cycles. That's how it basically organizes how it's doing something. And it's something that you have to deal with yourself in assembly, because if you take a lot of clock cycles, it's a slower program. If you can come up with a way of doing the program faster in less clock cycles, it runs faster. Just like when you do the high-speed poke, and the computer's running faster, your clock is running faster. It's making the CPU run faster. Gotcha. So these clock cycles are important. Of course, the real limit, as I mentioned before, on the 6809 CPU is you have a limited number of internal registers to store stuff, and you have to just design your program around those issues. Why don't we go ahead and go to the next slide? Oh, there's a lot of good advantages of the external RAM. You can store up to 64K. We're going to be looking mostly at the Coco 1 and 2 and how it does things. Coco 3 has got some extra hardware that can do more than 64K, but basically we're looking at internal 64K of RAM. Now the internal index registers can be used to point to RAM. See, like when you're looking at using the registers in the 6809, you say a specific register or specific bit of information. But if you're using an index register to point to a memory location and do stuff, similar to the way you do a peek and a poke, You can peek and poke in BASIC using an absolute number like hex 71 or something. But you could also use a variable to point to the location. Well, the registers are kind of like that. It's using a variable to point to a memory location. Of course, the disadvantage is it takes more time to get that information out of there. An INC RAM location, where you're incrementing a RAM location, typically can go up to about 4 bytes, depending on how you're doing it, and it can be up to 8 clock cycles. So depending on what you're doing, you're actually looking at situations where it's taking 4 times longer to do the instruction. Let's go ahead and go to the next slide. What I've got on the screen, and don't let it scare you, is actually some instructions in assembly language. One popular instruction is increment. Because one thing that we'll constantly do in the CPU is we'll add just 1 or subtract 1, the number 1, from whatever we're doing, whether it be internal register or memory location. So instead of having to sit there and say the command add 1, which has a lot of, it's a longer instruction because it's got the data in there, there's the increment and decrement registers, which help a lot to speed up the program because they're simple and they do that. In the case of increment A register, it's only 1 byte long, takes 2 clock cycles. Now, if you want to sit there and specify any memory location in the 64K, that's where the INC extended mode comes in. That's below that. And you can see by the table there, it is 3 bytes long. It's a lot longer than what a inking an internal register is. So since it has to go out to the memory to get all 3 bits of the instruction, it's a little slower to execute. Now, one of the things that they try to do with microprocessors is come up with ways to make things smaller, is they have something called DP or direct page. This is, in the beginning, it was always the first 256 bytes of memory. And the 6809 allows us to make that direct page, this special 256 bytes of memory, anywhere in the 64K. So when it wants to do this, let's say INC memory location 85, it's those 2 bytes there. As you can see, it only has to do the address and the actual instruction. Much shorter. And the final one down, and the final one down below is one of the ones that gets really big, that 4 bytes. We're incrementing something off the index register. And so you have the instruction, then you've got the index mode. That's what that the 6, I can't see it on my monitor, it's 86 or whatever it is. That tells it that's using the X register, and it's going to sit there and offset it by a 16-bit number. And then the next 2 is 04 and 00, that represents 1024. So that's the thing that we're going to be playing around with in upcoming lessons, is figuring out the best way for you to access RAM for that particular instruction you're doing. But I just want you to get an idea. There's different ways to access information based on what you're trying to do and the pros and cons of it. Some of them are really fast, like the INC A, because it's talking to the A register inside the CPU, so it's incredibly fast. But you can get ones that, like the INC A, the INC at, well, off the index register down at the bottom, that can take up to 8 clock cycles to execute.
Wow.
And it can be a lot slower. So there are balances you can do to things to speed up stuff and like that.
One thing I wanted to mention on the INC 10184, just to make it a bit more clear, maybe for some people, you were mentioning before you can use index registers as like a variable. Like you want to load a memory location like X equals 1000, peak X gives you whatever's in location 1000. In this case here, it's actually combining a math add and a variable. So it's taking X plus 1024, and it's getting the it's incrementing whatever's at that memory location combined.
Exactly.
So if X was 1,000, it's 2024 is where it's actually going to go. And that's one of the powers of the 6809 is you have all these extra addressing modes and stuff here. You don't have to like pre-add X and do all this other kind of stuff and then go to it like you have to do on some of the older CPUs. You can actually do this all in one instruction. So while it looks like it takes a ton of extra time to do, it's actually probably still faster than having to do X equals X plus blah, 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 then inc X type thing. So just wanted to put that.
Yeah, if you're trying to do the same thing 68502, where you got a 16-bit offset like what we're trying to do here, that could actually be close to about 3 or 4 instructions instead of one instruction. So a lot of people sit there and say 6502 is really fast. I go, yeah, but you're very limited on how you can do it. So the 6809, that's one reason why I've always enjoyed programming the 6809. It was never about trying to find some way to do something. It was trying to find the best way. There was always an avenue to do something. And you just would just write. As you got used to the 6809, you would write better and better code that was more efficient. But you could get in something in there pretty sloppily, and it'll work, but then you've got to go through and make it a little bit more efficient. But, yeah, why don't we just... last little slide here is talking about, next lesson is going to be on the memory addressing, really understanding how we're trying to use these address modes, what they are, what's the best case scenario for doing a particular operation. And as we go through the series, we'll actually get into the instruction sets, trying to use the instructions to do different procedures and like that. So this is going to be baby steps. We're taking it very simple and very slow. And now, let's hear it from the peanut gallery. Does anybody have any questions? And I'm sorry, I haven't been following the sidebar chat.
You just mentioned that the 68,000 had 16-bit registers, and technically they're 32-bit. Just that comment.
Yeah. Yeah, they're 32-bit. You can use them as 8, 16, and 32-bit registers.
Yep.
Yeah. It was definitely a lot easier to access a lot of memory with the 68,000 than it was with the 8086 processor.
Oh, yeah.
You don't like segmented memory?
That's the whole thing. It
was a sloppy rendition of 16-bit.
Yeah. And, that's the problem. It is sloppy. Well, they're trying to be efficient on the instruction set. I will grant them that, but it made it hell. Basically, what they did is they put a memory management unit into the CPU so it could access more than 64K of memory. And in their wisdom, the way they set up, the maximum amount of memory you could access on the 8086 was 1 megabyte. That doesn't seem like much these days, does it?
No.
I guess back then it did.
Well, it's just like they put 64K on the original PC, and then they said, "Oh, you'll never need more than 10 times that amount of memory." So they
even reserved like 384K for I/O, didn't they?
Yep.
On the IBM itself.
And back in those days, there was a way they would put 1 meg of RAM in there, and they would do stuff to kind of window it in. So we had all these special boots so you could play your games, because those programmers would never work within the spec of how much memory was on a typical machine. No, they had to get extra memory because they couldn't code it efficiently enough to use the memory that was there. Now, Rick will definitely agree with me. When you were coding on the Coco, you knew how much memory you had. You had to make it work within that memory, and that was it, right?
An interesting side note is that I noticed in the code for Shanghai, there's a little code on startup to see how much memory the game is taking, and if it's more than will fit in the cartridge, it dings a little bell. And that was while I was developing it, so I could tell, oh, you made it too big.
Yep.
And that's in the actual, production cartridge. It'll never ring, but it's there.
Oh, Rick, if you had any copy protection on there, the patches they would use more memory. I definitely had a few of those.
Yeah, I never really put in any copy protection. For Shanghai, actually, they asked me for copy protection, and I didn't want to do it. So after they mentioned that they wanted it, I didn't really say anything, and it never came up again, so there isn't any.
Yeah.
I had somebody email me once. He was a famous guy in the community who liked to crack copy protection. He said, "You're no fun."
I think I know the guy that you're thinking of. He's the guy that came up with the crack for the first version of Zaxxon.
Actually, one thing, Steve, I wanted to mention, because it's kind of ironic with you, is that one of the forms of copy protection for ROM cartridges was self-modifying code, because you try to overwrite the ROM. Of course, if you're trying to overwrite read-only memory, it doesn't do anything. But if you've copied it to RAM, you're destroying your own program as you go.
Mm-hmm. And the funny thing is, my random number routine actually would be used to try and write to the ROM, so it would randomly kill memory. So every time it happened, you had nothing to really show where the copy protection code was. It wasn't like there's a big thumbprint up there saying, "I'm doing this." It was a lot of random. But we had to do it because piracy was a big problem back then.
Oh, yeah.
Yeah. I just find it ironic, because you're not normally a supporter of self-modifying code, yet that would be the one case.
Yep.
Any other comments, questions, added thoughts about what Mr. Bjork has already presented to us? And remember, we're trying to keep it light for right now, but definitely for those of you who've got some insider knowledge, if you want to.
Well, did you understand everything, Steve? I guess you want to have yourself as kind of
yeah. So some of the because what I like to do is for me to grasp a concept, I try to find a metaphor for something else that I already understand and say, is it like this? And so some of the stuff that I was seeing with the registers versus RAM is very similar to some concepts we have on the modern CPU. For example, like a CPU now has got like L1, L2 cache, which is internal memory that makes things run faster than having to go out to the system bus and talk to RAM. So these concepts have obviously existed for a very long time. And you want to be, and some of these things have to do with the laws of physics, right? How quickly can a circuit travel? And so obviously inside the CPU is always going to be the fastest communications, because it doesn't have to go out through trace wires to then have some speed limits on it. So electronically, I kind of get that. Another kind of analogy was making me think of this is kind of like when you have real RAM versus virtual RAM, right? So you want to try to have things in real RAM because that's faster, but sometimes you got to go out to virtual RAM on an old Windows PC, and then that slows things down. So the more you can keep it internal and keep it electronic and keep it in a core, the faster it's going to be. But
exactly.
the amount of space you can fit it's a very small box. So you've got speed, but you've also got size constraints on how much you can hold in that small, fast box, right?
Yep, and that's actually a very good analogy with the caching thing, because like a level 1 cache versus a level 2 cache is kind of like the registers versus memory.
Yeah.
In a very coarse way. And I mean, people sometimes ask, well, why didn't you just put it all in the CPU, make a 64K RAM built in the CPU, all running at that really fast speed?
Right.
Well, cost and the footprint of the chip, complexity, a bunch of things come into play there.
Sure. Yeah, when I used to explain cache to my students, I'd always say, like, it's like, when a plane crashes, the one thing that survives is the black box, right? And so you might just say, well, why don't we make the entire plane out of whatever they make the black box out of, and it would never get destroyed? Well, the problem would be is the plane would be so big and heavy it would never get off the ground, right? So you got to have a compromise. So so there's like certain things. Some of it has to do with physics and the engineering, and then ultimately the consumer cost to produce and sell these products. So there might be a better way to do a circuit or do a chip, but it's not necessarily a consumer product at that point. A super processor with an all-in-one chip would be great, but it'd be very expensive to design and produce and purchase, right? So,
yeah.
And then the company would go out of business because nobody would buy it.
Right. Well, nowadays, aren't there like a bunch of these things they call this a single board computer or a single chip computer now, where everything kind of is, and isn't that kind of like what an FPGA is, where it's really just one piece of hardware now, or no?
Well, the FPGA is programmable, whereas if you buy a single board computer, it's already set up to do a certain function. So, but yeah, they're similar in being on one board.
Yeah.
Well, one of the things for like microcontrollers are used in like the Raspberry Pi and stuff like that. In a lot of cases, they don't have cache. What it is they got the CPU running pretty fast as it is.
Mm-hmm.
And if you add cache, that takes power. Power creates heat.
Mm-hmm.
And then you got to run the whole thing slower.
Mm-hmm.
So they're more interested in running that processor faster
Sure.
by keeping down the amount of silicon.
It's kind of like RISC versus CISC, because that was the same reason too, is to simplify the design of the chip, reducing the instruction set, so that the chip wasn't as complicated. It didn't have as great of a command set, but you could ramp it up faster.
That's another reason why all these chips that are being used in cell phones and other applications where power is really an issue, where you're looking at battery life. That's why the ARM processor is used. It's very small silicon. It can run very fast, but it doesn't suck up that much juice. And another trick they're starting to do now is they'll have one core, which is like one CPU, and it runs really, really slow. And then it's got some other ones that run really, really fast. And the ones that really run fast do not get turned on and used unless it really is going to do something like draw on the screen or do something that's a lot of power. But most of the time when that phone is sitting in your pocket, it's using that slower CPU and sucking almost no power.
It's almost like a turbocharger when needed, right? So
exactly.
And they're also making some cores specialized, so they only do certain things really well, and they don't have the general silicon to do everything a normal CPU would do. They're specialized to the point where they take less power to do some things that do require a lot of speed, but don't need all the functionality the general CPU has.
Yeah, it's that's the thing is, for a while there, it was just big companies like Motorola, Intel. They were designing these CPUs.
Mm-hmm.
And now you've got actual manufacturers design their own CPUs.
Sure. Apple.
They can go, and the thing about ARM CPUs is you can go to the company and say, hey, could you design me a chip to do this? They'll design it. And then you go to a manufacturing house and you just build it yourself.
That's pretty cool.
Yeah.
Kind of an a la carte processor if you need a special function or something, huh?
Yeah. But yeah, in the old days, CPUs were designed by a few companies. And of course, the other thing I've also said too, in the era of the time, the 6809, they were designing the CPUs for the guy that was going to have to work on the software and the hardware of the computer. And so they had to make the chip so that you wanted to work on.
Yeah,
and
the 609 in specific, the designers actually had been working with software designers. That's where they came up with the indexing modes that the 609 has that almost no other 8-bit CPU has, to make it easier to write compilers and assemblers and other high-level languages.
Yeah, so that's the whole core was they were trying to design something that I would like to program on. And guess what? I really like programming on the 6809.
Well, I hear a lot of people say that, and it gives me a good feeling to know that, I can't wait to follow in these footsteps. Everybody who's worked on it has said it's like that was their favorite 8-bit processor, and these are people who I have no reason to doubt for that. So I'm definitely looking forward to that journey myself, too, which will be just, hopefully a day or two away as I start learning it, too. I would like to just kind of quickly acknowledge some of the live chat that's been going on the side here. Some discussions were taking place during your presentation and after, and I'll try to catch up. And so let me first start off by saying, if I didn't say hi to everybody in live chat, I think we said hi to Paul Thayer earlier. Ed Snyder, the Zipster, is here. One of the questions that came up, starting with Terry Steen, and I don't know if we'll get into that later today or save it for another topic, but when we actually talk about what assembler do you use, and then so some people started chiming in where Paul Thayer says, I use LW ASM, which is Lost Wizard Tools, right? That's William Astle's tools. Ed Snyder says, yeah, for cross dev, he uses LW ASM. Ed Snyder saying hi. Mark Overhost says we could have a whole show just dedicated to cross assemblers, and maybe we should at some point in time. David Phillipson said I actually use the CSC cross assemblers I have for the 6801, 6809, 6502. Paul agreed with Mark. Boyson says hi to Ed. Ed says hi to Boyson. Terry Steen, I've not been in the public arena for a while. I figured it'd be a good source and a good assemblers out there, so he wants to know what to use. So we're getting some feedback there. Evan Wright's here, another assembler guy is here. Hey, Evan Wright. Nick Marotta says hello. Al Hartman is here. Hey, Al Hartman, how are you? What else did I miss here? There's so much text going on here. Evan Wright says hi all. Nick Marotta says hi. Terry Steen just started assembly language lesson. Wayne Aaron, thanks for ordering the Coco SDC. Eddie Serbinski is here. Hey, Eddie. Dave Phillipson says another handicap of the 6502 is that the X register is only 8 bits. Mark says all registers are 8 bits. Boyson says 6502 is Retro Innovation's favorite CPU. We got the Troll Junior's trolling Troll Senior here. So
yeah,
okay,
it speaks volumes of his character.
Tom C is here from Jersey. How's you guys doing? Nick Marotta says, would self-modifying code be a good copy protection scheme? If the game is on cartridge, it's okay, but if it's RAM, it kills itself. I think we answered that, right?
Mm-hmm.
Eddie Serbinsky is asking if the assembly language clips could be available separately. That's a question for Steve Bjork, if he wants to address that, if we want to make it as a mini clip. I'm not sure about that.
Yeah.
Now we're mentioning some books. Okay, I think I'm caught up on the chat there.
Yeah.
Sorry about that, guys.
I did want to add something about my copy protection. I wouldn't really call it self-modifying code. I call it self-destructive code.
Yeah.
Well, I think you've kind of mentioned that's what you view self-modifying code as anyway, right?
Exterminate. My Skype is just frozen. Uh-oh.
I guess Skype's using self-modifying code or emulating
self-modifying code. All right. So we're trying to baby step through assembly. We're not going to try to get too deep. So far with these discussions, I'm able to follow it. For those of you who are not assembly folks like Grant, was this pretty good for you too, Grant? You're muted.
Sorry about that. Yeah, it's easy to follow. I'm starving for some more, but we'll have to be patient. But
kind of like Coco Forever. You got to binge this stuff, huh?
I'm on that Generation X/Millennial. I want to binge it all at one time and get it all done. But
yeah.
But I think you're right. My brain would probably blow up just like yours if we did.
Well, it reminds me of a recent episode of The Next Generation where they were observing a civilization that wasn't quite as advanced, and they were telling them, listen, we can't give you all this information. You need to discover this at your own pace. And so that's kind of where we are right now. We have this advanced knowledge that's out there, but we have to evolve. Where am I going with this crap? I don't know. But yeah, so
it's helpful preventing
he had a
yourself from
good
destroying
train of
yourself.
thought. It just went off the rails. That's what happened.
Yeah.
Where is that train? I don't hear the train.
Where did that train go?
Hey,
Oh,
Steve.
that's not the train. That's not the train. Hold on. Where is that train?
Jackhammer going.
And this is James Diffendaffer's background theme music here. There we go. There's that train. All right. I hear that train a-coming. All right. Well, have we covered enough on this for now? Okay.
Absolutely.
All right. So here's what we're going to do.
I
Go
will
ahead.
say this thing. The lessons will start getting more meat as we go forward. This is just the foundation area. Then we'll actually start getting into instructions. The next one's addressing modes. It's kind of crossing the line between foundation and true assembly. So there'll be a lot of meat for the next one.
Okay.
Take your aspirin before we start.
This concludes another episode of Coco Talk, the world's leading live talk show featuring the Tandy Color Computer. For all things Coco Talk, visit us on the web at cocotalk.live. We'd love to hear from you. Send feedback, suggestions, even segments via email to cocotalk@cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Consider supporting the show with a purchase of merchandise from our retro swag shop at 8bit256.com. If you'd like to become a patron of the show, click the Patreon link at our website at cocotalk.live.
Cocoa Talk is rocking the 8-bit world, keeping the tandy flame alive. We may be mocked, but we'll never stop, 'cause Cocoa Talk is rocking the 8-bit world.
Cocoa Talk would not exist without the community, its cast, crew, and contributors. Thanks go to Curtis Boyle, David Ladd, Mark Overholzer, Grant Leedy, Bruce Moore, Nick Marentes, Ron Delvaux, Rick Adams, Jason Reichert, Richard Lorbieski, Jim Brain, Tom C., Rob Inman, Mark Bosley, Brian Joyce, Ken Reichert, David O'Connor, Brian Weasler, Terry Steggy, Nick Marotta, John Strong, and many more, especially to Steve Bjork for production suggestions and James Different-Daffer for making my head explode. Please help support the Cocoa community by visiting some of its various contributors. A list of resources is available at imacoconut.com. That's imacoconut.com. The Cocoa Talk theme song is copyright 2008 by D. Bruce Moore and Greg Sheeler. Mixed, mastered, and produced by D. Bruce Moore.